Now that we know more about solving linear equations, we want to talk about how can I apply them to real life situations. So predominantly this section is going to be word problems. So what I want to do first is go over kind of a strategy, just when we're dealing with word problems in general. So the first and foremost thing you have to do is you have to identify, what are you being asked? What do you need to find? So you might need to make notes, you might need to draw a picture. You can have a lot of information that's thrown at you in a very short matter of time. Or on the other side, you could have a very long statement and you need to just pull kind of the most important info from in there. So do whatever you need to that can help you kind of organize that information better. You're always going to be looking for some unknown quantity, so you want to assign a variable to that unknown. Like there might be multiple unknowns, but the thing you specifically are being asked to find, make that the most important variable. Typically we use X. Fourth thing we do, you want to set up an equation and solve, and really there's no rhyme or reason. It's just going to be very problem specific for what you need to do. And then the last thing you should always do anytime you solve some kind of problem is check your answer. And what I mean by that is just ask yourself, is it reasonable? You're giving a real life word problem. If you find out that you need to invest negative money to make something, you've made a mistake somewhere. If you are mixing stuff together and you need like 5 gallons of one thing and then 1,000,000 gallons of another, probably something off there as well. You just want to see, like, is this reasonable for what I've been asked? Okay. So one of the most important types of problems we're going to do are mixing. So if you've had to take a chemistry class, you've done something like this before. Concentrations only come in certain percentages, but to do some kind of experiment, you need a percentage you don't have. So we're asked, how many gallons of a 5% acid solution must we mix with 5 gallons of a 10% solution to obtain something in the end that's 7%? So again, very, very short statement, but a lot of info thrown here. So what I tend to like doing for these problems is I like to draw myself a little picture. So I've got one bucket, I'm adding to it another bucket, and in the end, I'm getting a solution over here. And so each of these I'm going to label just by the amount of acid that's in there. We're mixing together something that's 5% acid and 10% acid. And in the end, I want to get something that contains 7% acid. Okay. The only thing I know for certain is that I have 5 gallons of this 10% mixture. So right down here, I know I have 5 gallons. The other two, no idea how much. But the thing I'm specifically asked is how many gallons of a 5% acid solution must we mix? So this one is the most important one. That is what I want to find. What is X? How many gallons? Okay. So the only thing I'm missing now is then how many gallons of this final mixture do we have? So kind of think of it just in terms of numbers. If I need 7 of this, I have 5 of this. In the end, I have 12. If I need 9 gallons of this, I'm mixing it with 5 gallons of this, I have 14 gallons in the end. So no matter what I do, the amount of gallons we have is we add the two together. So really it results in an expression, X plus 5 gallons. Okay. So if you can draw this picture, you can come up with the equation that you want, and then you can solve for that unknown. Because really the amount of acid when we mix it is never going to change. By mixing these two structures, for the first one, 95% of that is likely water, 5% of it is acid. 10% of this solution is acid, the rest is that water substance. And then same thing over here. I'm not going to create new acid. So what I'm going to do is I'm going to create an equation that tells me the gallons of acid I have in total. Okay. So I'm going to start with this middle mixture. I have 5 gallons, 10% of it is acid. So what I'm going to do is I'm going to take the 5 and I'm going to times it by 10%, just 0.10. Okay. For this next one, I have X gallons, 5% of it is acid. So I'm taking the total amount of gallons and I need 5%. So this gives me the amount of gallons of acid in the 5% solution. And then on the right hand side, I have X plus 5 gallons, 7% of it is acid. So I'm going to take the amount of gallons we have and times it by 0.07. So what this has done is it now tells me the gallons of acid from the first mixture plus the gallons of acid from the second is equal to the gallons of acid in that final 7% mixture. So we've created an equation that has just a single variable X. We can now solve for it. So I'm going to clean this up just a little bit. This is 0.05x. If you do 0.1 times 5, that gives you 0.5. And then on the right hand side, if you distribute this out, that's 0.07x. And then 0.07 times 5 gives us 0.35. So we really have a decimal equation. You can multiply by 100 to get rid of the decimals if you want. That works too. But now I need to get x's on one side, constants on the other. So I'm going to subtract the 0.05x. And so that leaves us with 0.5 on the left. It gives us 0.02x on the right. And then this 0.35. Then we need to subtract the 0.35 over. So we're left with 0.15 on the left, 0.02x on the right, dividing by 0.02, then gives us our final answer of 7.5 equals x. So we need 7.5 gallons of this 5% acid mixture. Okay. And so again, I'm going to ask myself, is it reasonable? I was mixing 5 gallons of this solution. 7.5 isn't too far off to give us a concentration somewhere in between 5 and 10. It seems pretty valid. Again, I can't check immediately that yes, I did this 100% correctly, but it's not something so far-fetched. If it wasn't, or if it was something that was really far-fetched, you probably made like a tiny mistake somewhere, or you'd have to go back and try that setup of the equation again. Let's try a similar one, but now we have something that's pure alcohol. So we want to figure out how many gallons of pure alcohol must be mixed with 10 gallons of a solution that's 20% alcohol to make a solution that's 50%. So again, just a mixing problem. I've got one solution, adding another, and in the end getting a final mixture. So the two solutions that we're adding together are pure alcohol, so that's 100% alcohol. The other one is 20% alcohol, and we're getting a solution that is 50% alcohol. Okay. I know that I have 10 gallons of 20% alcohol. So immediately underneath we can put 10 gallons. Okay. We want to know how many gallons of pure alcohol. So I don't know what that is. This is our goal though, so I'm going to call it X. And then same thing on the right hand side to figure out how many gallons are in this final mixture. We just add the two together. So in total we'll have X plus 10 gallons of this mixture. So creating our equation, we have 100, which is 1 times X. 20% is 0.20 times 10, and that gives us 0.50 times X plus 10. To show you just another option as to what you could have instead of doing the decimal forms, you really can use the numbers. So you can say 100x, 20% to leave it as 20, 50% leave as 50. That also works, and you'll end up with the same answer. So to do this, we've got to distribute this out, and we can do the 20 times 10. So this gives us 100x. 20 times 10 is 200. And then on the right hand side, we get 50 times x, and then 50 times 10 is 500. So getting an x's to one side, we subtract the 50x, subtract the 50x, and that still leaves us with 50x plus 200 equals 500. And then we subtract the 200, and we're left with 50x equals 300. Finally, dividing by 50 gives us x is equal to 6. So we need to add 6 gallons of pure alcohol to the 10 gallons of the 20% mixture to get the desired mixture we want. Let's try one more word problem. We're told a tree cast a shadow that's 45 feet long, and at the exact same time, a shadow cast by a vertical stick that's 2 feet high is 1.75 feet long. Our goal we want to figure out is how tall is our tree, and we want to use similar triangles to do this. So I'm going to draw a little picture. We've got our tree, and it is casting a shadow. Then we also have a stick, and it is casting a shadow. So I'm trying to do that one a little bit exaggerated. Okay. And we're told to use similar triangles, so I'm actually going to create a triangle in each of these. Here's how tall our tree is, how tall the stick is. Because if we have our sun over here, it's casting the shadow, and it creates these two similar triangles within it. Okay. So filling in the pieces that we do know, we know the shadow of the tree is 45 feet long. We know the stick is 2 feet high, and its shadow is 1.75 feet long. Okay. So because this sun is really hitting the same spot on both of these, it creates two triangles where these angles are exactly the same. So the triangles are basically stretched up versions of each other. And what I want to do is I want to figure out what this side of the triangle is. So I'm going to call it x. That's the height of our tree. When we're dealing with similar triangles, we know that because there's this scale up, the ratios of similar sides must be equal. So if I take x and divide it by 2, it's got to be exactly the same thing as 45 divided by 1.75. And you can really kind of keep this any way you want, but they're proportional. I've taken all sides of my stick triangle and I've multiplied them by the same number to get my tree triangle. So we're going to set up a proportion. You can stay consistent as to what you want. Really makes no difference at all. So I'm going to go ahead and keep these sides on one piece. So here's the stuff that's coming from the same side. So I'm going to put x in the numerator, 2 in the bottom. So when I'm dealing with this second fraction, I want to stay consistent. These are still going to be the same side of the triangle. But in the top, I put the variable that was dealing with the tree. So I want to do the variable in the tree up top. And in the bottom, I want to do the side from the stick, because that's what I put in the bottom over here. So from our tree, the one side length is 45. The corresponding side for the stick is 1.75. So it keeps everything consistent both vertically and horizontally. Okay. So we're able to set up this proportion that we want to solve. So really, you can cross multiply. So that gives us 1.75x is equal to 45 times 2, or 1.75x equals 90. And then dividing by 1.75 gives us that x is equal to 90 over 1.75. And unfortunately, it's not a nice number. So your directions in your homework will say to round to however many decimal places. It's about 51.43 feet. Okay. You also didn't really need to cross multiply on this problem because we really had x over 2. So a simpler way was back at this step, I could have multiplied this side by 2 and this side by 2. So those would cancel, and that gives us x is equal to 45 over 1.75 times 2, which still will give you the same answer. Okay. So the second topic we're going to go into here, this actually relates to the last problem. It's this concept of direct variation. And so all it is a very specific line. We say a number y varies directly with x if there exists a non-zero number k such that the variable y is some constant times x. So this constant is called our constant of variation. The best physical example you can think of is Hooke's law. So if you've ever taken physics or a physical science class, it really is something that deals with springs. So what it states is the distance y an elastic spring stretches beyond its natural length varies directly with the amount of weight x hung on the spring. So what this means is if you have one weight attached on, if I make the weight a lot larger, it's going to stretch the spring a lot further. So here's my spring in its natural position. When I attach a weight on it, it's going to stretch those coils out. Here's the weight. And then if I attach a bigger weight, maybe like twice it, it's going to go twice the distance down. Okay. So this constant of variation is really also called our spring constant. Just depends on the spring, the type of material, lots of factors within it. Okay. So we want to figure out if a force of 15 pounds stretches a spring 8 inches. If I then put a 35 pound on, how much will it stretch the spring? So I'm going to do this 2 different ways. You can go about it either way that you want, but we know that this thing varies directly, so we're going to actually come up with the equation for it. So we're told when we put a weight of 15 pounds, the distance it stretches is 8 inches. So we can come up with this equation and we can solve for k. So plugging in our pieces, y is 8. We don't know the constant. X is 15. Divide both sides by 15. And this tells us our constant of variation is 8 over 15. So the equation that represents this particular spring is 8 over 15x. So what we want to answer now is how much will a force of 35 pounds stretch the spring? So all we're going to do is replace x by 35. So the distance it stretches y is 8 over 15 times 35, which is going to give us 280 over 15, or about 18.7 inches. And again, we can see this is relatively reasonable. I went from a 15 pound weight to a 35 pound weight. It was a little more than double. So my distance went from 8 to about 18.7, a little more than double. And now again, you don't need to set up a direct variation equation. Direct variation is the same thing as directly proportional, so we can set up a proportion. For the one instance, we stretch 8 inches for 15 pounds of weight. And that's going to be equal to the same amount that we stretch on the other side. So we have a 35-pound weight, and we don't know how many inches, so we call it X. So really it's the same thing as solving, or let's call it Y, because that's what we were given before. We just need to solve this equation for Y. And to do that, again, you can cross multiply and you'd see, but really you can times this side by 35, do the same thing over here, and you end up with exactly the same equation. Okay? So direct variation is another way to just say things are directly proportional. Very specific type of linear equation. Okay? So we have one last thing that we have to do. The other application is if we have some formulas, you've used them in any of your math classes before, some of your science classes. We want to try to manipulate a formula for a given variable. So what I want to do for these, especially in this first one, we're given this formula, V equals LWH, it's just the volume of a box. I want to solve this equation for L. So I want to get L by itself. You might have a couple different ways. This problem doesn't. So kind of go with your gut. The one thing you want to avoid is you don't want fractions within fractions. So to get L on its own, I need to get rid of these other two things. And right now, LWH means L times W times H. So to get rid of these two, I want to divide. So I want to divide by W and I want to divide by H to make them both cancel. But what I do to one side, I've got to do to the other. So L is really equal to V over WH. So we have solved this equation for the specified variable. The second one, a little bit more annoying. We want to solve this equation for little b. And if you've ever seen this equation, it's actually the area of a trapezoid. The height is the distance between the two parallel sides. B and capital B are the bases or the parallel sides. But I have a couple routes that I can go with this one. What I would recommend, because we have this 1/2 out front, is I would say let's try to get rid of this. So if I take this and multiply it by 2, that's going to make both of those cancel. But what we do to one, we've got to do to the other. So we've got 2a on the left, and then h times b plus capital B on the right. Okay. If you want to distribute the h at this point, you can, but really you want to get this on its own. This is standing in our way, so let's get rid of it by division. These two things are being multiplied. So I'm going to divide both sides by h. So on the left-hand side, we have 2a over h. And on the right, we have little b plus capital B. One last step, I've got to move this over. So I've got to subtract b. So that leaves us with, gonna go up here, 2a over h minus capital B equals little b. And that has manipulated our formula for little b. Another thing you could do is instead back here, if you didn't like dividing by h, do this off to the side. We ended up here. Maybe your gut said distribute these to get rid of the parentheses, perfectly fine. So that gives us 2a is equal to hb plus h capital B. And then I've got to move this to the other side. So on the left, I can't do anything with those. I just have to leave it as 2a minus h capital B equals h little b. And then we divide by h. So we get little b on the right and 2a minus hb over h on the right. Both of these are exactly the same thing, just a slightly different version of each other. Right? So you have lots of roots that you can take. Again, go with your gut instinct. It might take you a little bit longer, but it's going to lead you to the same place.